So maybe we'll start. Good morning, everyone. So as always, if at all you have any questions in middle of the talk, you can unmute yourself and ask directly. Today we have Professor N. Narayanan from IIT Madras, and he'll be talking on Shitov's disproof of Hedetniemi conjecture. Over to you, sir.
Okay, thank you for the invitation. So this, this Hedetniemi's conjecture has been open for like something like, I don't know, 5 decades or maybe slightly more. And several attempts were ongoing, and but most of the time, like people were trying to prove it rather than disprove. I think there were some attempts to disprove. And there are several results, like which says that okay, this class of graphs satisfy this class of graphs satisfy conjecture, etc. in the positive direction. And it was very surprising and interesting to see this result, which was submitted last year by Shitov, which is just one page, proof. I mean, so the what he submitted was like so his entire paper is 1.5 pages, and half of it is like introduction and references. So what remains is just less than 1 page. And when this paper came, I took a look at it, and then I it was kind of difficult to follow. So I did not really spend much time on it. But then fortunately, I went to meet Professor Zhu in China for some time, and he told me that like he was asked to give a presentation because many other people were finding it tedious to read. So he was preparing a talk, and he was going to give a mock talk to us so that we can just attend it. So I attended this lecture by him, and it is from these notes I prepared this slide. So it was a very nice lecture, and I think his lecture is available on YouTube now. So what he gave later in Taiwan. So anyway, so that is the story how I came to this, and because I liked the lecture very much, and the proof is reasonably simple, even though it is written very cryptically. It's a nice proof. So let me go into it without further ado. So the outline of the talk is something like this. So we will look at the conjecture. Then very important object in the study of Hedetniemi's conjecture is what is called exponential graph. So we are going to define what is this exponential graph, and then some properties. And then we look at this graph, G times the exponential graph, the direct product of G and exponential graph. And we will show that this product can be colored with C colors, no matter what the chromatic number of G or exponential graph ECG are. So now the idea of the proof is clear, like to show that there are some graphs G with chromatic number larger than C, and whose exponential graph also has chromatic number larger than C, then it is going to violate the Hedetniemi's conjecture. And the proof follows by starting with the classic result of Paul Erdos. that there are graphs with arbitrary large girth and arbitrary large chromatic number. And then what remains is just to show that this ECG has a chromatic number strictly greater than C by some smart way of counting. So that's all the proof is about. So let us look at the. I think that there is some problem, Suchita.
Yes, sir. What is?
So the problem is that, I get to these messages of people trying to get admission, and once it comes, my keys doesn't work. I have to use the mouse. So I don't know why it is happening.
Okay. We'll just change the settings accordingly.
Okay.
You're also co-host. That's why it's popping on your side.
Okay.
I'll just change that.
Yeah.
Sorry about that. It's
So,
done now.
so you have two finite simple graphs, let's say G and H. Okay. Now, the chromatic number of a graph, as we all know, is the minimum number of colors, such that you have a coloring of the vertices of the graph where adjacent vertices get distinct colors. Now, the direct product of the graphs G and H is a graph with a vertex set as the Cartesian product of the vertices of the graph, vertex sets of the graphs, and two vertices, let's say GH and G dash H dash are adjacent if and only if G dash is an edge in the graph G and H dash is the graph, edge in the graph H. So here is one example, like you have C3 times P4, and if you look at if you just concentrate on just an edge from each part, you will see that the product of two edges is precisely a graph with this structure, like a cross. It's a disconnected graph, and that is the reason for the symbol, right? G cross H. And what one can observe quite easily is that the direct product of graph G and H can be colored with the chromatic number of G or chromatic number of H, whichever you choose. And this is very easy to see that if you take a proper coloring of, let's say, graph G, then I can give a coloring of the graph, the direct product, by just looking at the H fibers and give them the same coloring. Or in other words, I look at the vertex GH and I just color it with the color of G, whatever it is. Now, since the coloring was proper, we can immediately see that the coloring of the product is also proper, because whenever GH and G dash H dash are adjacent, G must be adjacent to G dash in G, which means that the coloring phi would give G and G dash different colors. So therefore, this is immediate. So now by symmetry, you have the same result for H. So by this thing, we know that the chromatic number of the direct product is at most the minimum of the chromatic number of G and chromatic number of H. And once you have this, the question is that can you do better? Can you do with less? And Hedetniemi conjectured that it is actually equal to the minimum. You cannot do better than that. And this is what we are going to disprove today. So one of the important objects in the study of this conjecture is what is called the exponential graph. So exponential graph of a graph G has as its vertices set of all C colorings of the graph G. Okay, so ECG. So you associate the positive integer C to define this. So ECG is basically the set of all C colorings, and C colorings need not be proper coloring. So it can be all arbitrary functions basically. Okay, set of all functions from the vertex set of G to the set 1 to C. And the two colorings are adjacent if they give distinct colors to adjacent vertices in the graph G. So if X and Y are adjacent, then phi of X must be different from psi of Y. So this defines the exponential graph. So the name exponential graph comes because of the number of colorings is going to be exponential, or the number of vertices is exponential. So we have this, right? So now the next observation is that whenever a coloring is proper, corresponding vertex has a loop over it, which means that it is adjacent to itself. And that is immediate from the definition, because proper coloring does not give adjacent vertices the same color. So therefore, this condition is satisfied. So that is going to be an edge. But what is more interesting for us is that no matter what your graph G is, G direct product with ECG admits a proper coloring with just C colors. So to see this, why this is true, let us look at the following coloring. I am going to give a coloring. It's just one line proof that if I take, let us say, a vertex, let's say U comma F, where U is a vertex in G and F is a function in ECG. What I am going to give this vertex is F of U as a coloring. Now F is a coloring from the of the vertices using at most C colors. So therefore, whatever coloring we are going to get is a C coloring. Now, why is this proper? Well, if you have UF and let's say VG, and UF is adjacent to VG in the exponential graph, then I want to show that they get different colors, right? Now, if UF is adjacent to VG, by the definition of the product, U must be adjacent to V and F must be adjacent to G. Now, if F is adjacent to G, by again the definition of exponential graph, F is adjacent to G if and only for adjacent vertices, let's say U and V, they will give different colors. So F of U is different from G of V, and that is the proof, right? So we get a proper coloring, and it uses at most C colors, so therefore it's a proper C coloring. So we have a C coloring for G cross ECG as far as whatever your G is. Is that clear? Now another observation is that the constant functions form a clique in the exponential graph, because constant functions are the functions which whose image is just a singleton. Now there are C such singletons because there are C colors which are allowed. So every vertex is mapped to 1, every vertex is mapped to C, etc. So these are the C constant maps. Now if you take two functions whose ranges are disjoint, okay, if two functions whose ranges are disjoint, then they are going to be adjacent in the exponential graph, because they are not going to give the same color to any vertex or any pair of vertices, right? So no matter whether it is adjacent or not, so they are not going to give the same coloring to any two vertices. So because of this, these vertices are going to be in a clique. These functions are in a clique. So if I take GA and GJ to constant functions, then GA of X is different from GJ of X. So that is the idea. So if the images or the ranges are disjoint, they are going to be adjacent. So this is which we mentioned already. Okay, so what else we have? So as we mentioned, the idea of the proof is now to come up with a graph G with a chromatic number greater than C, such that the exponential graph also has chromatic number greater than C. Now, whatever we have covered so far is already known in the literature. Before this proof was appearing. So these were all previous work, like people had studied exponential graph before. And the only trouble is to bring up a graph with this property that its chromatic number as well as the exponential graph's chromatic number is larger. Now the first part is very easy. We are going to come up with a graph using a very classic result of Paul-Erdős. So what the result of Erdős says is that there are graphs with arbitrarily large girth and arbitrarily large chromatic number. This is the way the proof is known, or the theorem is known. But but the proof actually shows slightly stronger result. It shows that there are graphs with arbitrarily large girth and arbitrarily large fractional chromatic number, or arbitrarily independence ratio, right? So the number of vertices by independence number can be arbitrarily small. So And once the the independence number or independence ratio is small enough, you can use the relation between the chromatic number, the number of vertices, and independence number to show that there is a large enough chromatic number. So we are going to use this result, and therefore we will come up with such a graph. Okay, so no matter what this graph is, you look at the number of vertices and call it as P. Okay, so you have a graph with these properties, and the number of vertices is P. So we are going to define a parameter as follows. In fact, we are going to define the parameter C and another parameter Q. So let Q be a number larger than 2 raised to P minus 1 into P square. Right? Now we should see that this is really huge number, because if you want a graph with girth 6 and the independence ratio P by 4.1, then one can verify that it has something like close to 200 vertices. So 2 raised to 200 minus 1 into P square, is going to be very large, and then our C is going to be even larger. It is 4Q plus 2. So we define these parameters Q and C. Then so you have this graph on 200 vertices, and now I am going to modify this graph by replacing every vertex of this graph with a complete graph on Q vertices. And then 2 vertices, if they are adjacent, then the corresponding clicks I put a complete bipartite graph between them. Okay. So this is the graph that I denote by G cross KQ, GKQ for short. So once I have this graph replaced by these clicks on each vertex, what happens to the independence number? So the independence number, we can see that independence number does not change, because from any click I can only pick one of the vertices for the independence number. So whatever was the independence number earlier is going to be the same, because I cannot pick anything more. So naturally the chromatic number increases, right? In fact, it gets multiplied by Q, and therefore one can easily see that the chromatic number of GKQ is greater than or equal to the total number of vertices P into Q by the independence number, which is P by 4.1. So therefore PQ by P by 4.1 is like 4.1 into Q, which is greater than 4Q plus T, because Q is large, and that is equal to C. So chromatic number of this graph is now strictly greater than C. This much we have, right? So now what remains is to show that the chromatic number of the exponential graph is also larger than C. If we can prove that, we have disproved the Hedetniemi conjecture. So the entire work now is to show that this is the case, that the exponential graph has a chromatic number strictly larger than C. Now, something that we already know is that there is going to be a C click, right? Click of size C in the exponential graph, right? Because all the constant functions, right? Constant colorings form a click, and there are C of them. So we can immediately see that if the chromatic number is not greater than C, then it must be equal to C. There is nothing smaller, right? Because we need all the C colors. So to the contrary, we assume that there is a proper coloring of the exponential graph using C colors. Now, because of this property that we just mentioned, we can assume without loss of generality that the constant map GI is given the color I. Why is this? This is because if you have a coloring, where I use all the C colors, right? So I use all the C colors on this click. Now, suppose I have a proper coloring of the graph, and where there is some vertices are colored red and some vertices are colored blue. Now, suppose I call all the red vertices as blue and all the blue vertices as red. I mean, it's not going to change anything about the proper coloring, right? So I can just rename the color classes to whatever I want, right? So as far as I do it uniformly across, this is not going to affect the properness. So I have this proper coloring. I'm going to just call whatever color class GI is mapped to as with the name I. And because all the C colors appear on the click, I can do it for all the colors. So now I know that every constant map GI is mapped to I itself by the coloring psi. Okay, so this is very important because it is going to help us, come up with some nice constructions. So a direct observation from this is that if you look at psi of phi, it is an element of the image of phi, right? The way we have defined it, psi of phi is an image of phi for any map in the exponential graph. And why is this? Well, suppose some color is not in the image of phi. I show that it cannot be used to color phi, right? So suppose I is not an image of phi, then because of the earlier property that we saw, that if the ranges of two functions are disjoint, then they are adjacent in the exponential graph, right? So phi is adjacent to gi because I is not an image of phi. Therefore, and gi takes everything to I, right? So therefore, their ranges are disjoint, and therefore they are adjacent. Now, if they are adjacent, a proper coloring cannot give adjacent vertices the same color. So therefore, psi of I is not I because I is proper coloring. Right? So therefore, if there is a proper coloring psi with C colors, then we have this corollary. Okay. So yeah. Now we are going to define what are called simple maps. So a map is simple if it so you obtain this graph GKQ by replacing every vertex of the graph G with a copy of KQ. Now suppose a coloring gives all these Q copies of a vertex the same color, right? For every vertex, all its copies, right, in the product graph GKQ get the same color. Then I call such maps as simple maps. Such colorings are simple. Okay, so basically, phi of u comma I and phi of u comma j are the same, right, for any I and j. Now, if they are going to be the same for all this, then I can as well call it as phi of u, right? In the product graph, this indices for simple maps, the second index is not required because once for one, for everything, right? It's all the same. So for simple maps, I can use this simplified notation. Okay, so now if two maps phi and psi are simple, then they are adjacent if and only if, of course, by the definition, for adjacent vertices they must give different colors because they are in the exponential graph anyway. So if u is adjacent to v, phi of u is different from phi of psi of v. Right? And second is that phi of u must be different from psi of u also. And this is because in this product graph, even though we use the simplified notation phi of u, it is basically phi of u comma something, right? Phi of u comma 1, phi of u comma 2, etc. All these. But since they form a clique in this product graph, now not the direct product, the GKQ, the replace graph, right? The expansion graph. So in the expansion graph, because ui is adjacent to uj, this coloring, if they are adjacent, they cannot be giving the same color. So therefore, if phi is adjacent to psi, then it will give a vertex also different colors, right? This adjacent functions will give the same vertex also different colors, adjacent vertex also different colors. This is a very very nice observation that if you have simple maps, right? If you look at all the simple maps, now the simple maps form a kind of you collect all the simple maps and look at the subgraph induced by the simple maps. The subgraph induced by the simple maps form a graph which is isomorphic to the exponential graph of G, but with a slight change that every vertex there is also a loop, right? Because we don't want these things to give the same color to the the copies of the vertices, right? And because of this phi of u and psi of u are different, so it's basically it is like there is a loop at the graph, every vertex of the graph G, right? I start with a simple graph G, now introduce a loop at each vertex, and then take the exponential graph, right? And then like the maps behave exactly like that. So the simple maps basically induces such a subgraph. So let me call by ECG0 the subgraph of exponential graph ECGKQ induced by the simple maps, where G naught is a graph with a loop introduced at each vertex of G. Okay. So so is it clear so far? Like we need these concepts in the following. So I hope that things are clear to all. I mean, maybe I'm going a little too fast. I don't know.
Does anyone have any questions? So maybe we can proceed. Like if there is any questions, people will ask.
Now, just to give an idea of like the size of the graphs that we are talking about. This graph ECGKQ is really huge, right? Because we already mentioned that the number of vertices in this graph with that we obtained from the Erdos result will have close to 200 vertices, and our Q and C are like exponential in, right, 2 raised to 199 into 200 square, right, which is Q, and then 4 times that is C. So basically, if you look at the graph ECGKQ, right, it has C raised to PQ possible colorings, right? The number of vertices is PQ in the graph, so the number of colors are C. So therefore, C raised to PQ possible functions are there, and this is like 2 raised to 200 whole raised to 2 raised to 200, something close to this. I mean, 2 raised to 200 itself is like so huge, right? Now this exponential to itself is extremely large, right? On the other hand, if you get ECG0, right, the subgraph that we are talking about is relatively small, right? It's like C raised to P instead of C raised to PQ. So it's like only 2 raised to 200 whole raised to 200, right? Much smaller compared to the graph. So we are going to deal with the smaller graph and show that this smaller graph together with a little bit more things is going to be not C colorable. Instead of the entire graph, there is a subgraph. We are saying that it is not C colorable. So that is what the proof is going to do. Okay. So for this we need some definition. So let us define I of B comma B as the set of all what you call like colorings or simple maps, set of all simple maps, such that the image of V under phi is B, and the image of phi under psi is also B. Okay. We can do this because we know that like psi of phi is in an element of IM of phi. So therefore, every every simple map must appear as one of IVBP, right? So if you look at all possible V and B, where V is a vertex and B is some color, then at least in one of the IVBs, this simple map must appear because of this property. So therefore, the vertex set of ECG0 can be written, the cardinality of IVB is greater than or equal to 2 into P into C raised to P minus 2. These are just some things that we will need. Now, the claim is that there is some vertex in the graph G such that for more than half the colors, in 1 to C, IVB is large, right? So more than half the colors B, IVB is large for some vertex B. See, the idea of the proof revolves around basically counting the simple colorings in terms of IVB. Okay, so now the idea is to show that, like, in idea is to restrict that the choices for certain vertices. Say that, okay, for some vertex in this coloring, some vertex has only one choice to count the coloring, and for some other vertex there are only two possible colorings, and then remaining, I don't care, I'll use all possible C colorings, and still I get a contradiction to the counting that we have. So we are going to do it in two different ways, right? So there is some vertex for which for more than half the colors IVB is large. So how do we prove this? Well, suppose not, then we will say that, okay, let S of V denote the set of all colors such that IVB is small for V. Now define a list of simple maps such that phi of V is an element of this set S of V, where S of V is the set of all colors which makes IVB small, right? So now collect this and form this list, and now I am going to count L in different ways. So one way to count L is to say that, okay, because S of V must contain at least C by 2, right? Because we said that, if it is, the large, IVB is large is strictly greater than C by 2. So if it is not true, then at least for half of them, for every vertex, it must be greater than or equal to C by 2, right? S of V must have at least half of these ways. So now I take the product over all the vertices. So product over V, S of V greater than or equal to C by 2 raised to P. So L is at least C by 2 whole raised to P, according to one counting. And then I can also count L by the property that, it appears in all this, in this union, right? So union over all possible V comma B, IVB is small. Now, if IVB is small, we know that the size of IVB is less than 2 into P into C raised to P minus 2. But now there is at most P vertices and at most C different possible choices for B. So therefore, this is less than P into C into 2P into C raised to P minus 2. But this implies from the earlier bound for L that C must be less than 2 raised to P minus 2 raised to P plus 1 into C square. But this contradicts the choice of C, because we set C to be 4Q plus 2, which is strictly greater than 4Q. But what is 4Q? It is 4 into 2 raised to P minus 1 into P square. So this basically is basically 2 raised to P plus 1 into P square, which is a contradiction to our assumption of C. So therefore, there must be such a vertex, right, with half of the colors makes IVB large. So choose V star to be such a vertex for which this lemma holds. So now we are going to only talk about vertices with this V star. Now we are going to define some more maps now, but these are not simple maps. Okay. So let T to be the set, let's say 2Q plus 1, 2Q plus 3, etc., 4Q plus 2, which is more than half of C. Okay. And we define mu T as a coloring such that mu T of x comma I is equal to I if the distance in G of the vertex X from V star is either 0 or 2. Okay, and it's Q plus I if it's 1, and T if the distance is at least 3. Okay, so it's a very smart way to define using these distances. We will see the use of this immediately in the next couple of slides. So of course, since we are talking about all possible coloring, such colorings are also going to be part of ECGK Q. Now let us say that for all this T you have mu T is defined. Now the claim is that this mu t's form a clique in the exponential graph also. Now why are they forming a clique? Because suppose they are not a clique, there must be some different t and t dash such that mu t is not adjacent to mu t dash, right? Now if two maps are not adjacent in the exponential graph, that is because for some adjacent vertices in the graph GKQ, xi is adjacent to yj, and xi is given a color by mu t, which is the same as the color given by mu t dash to yj. Let us call this common color as alpha, right? Now alpha must be in the intersection of the images of mu t and mu t dash. But what are the images of mu t? Well, images of mu t are I, q plus I, or t, and the images of mu t dash are j, q plus j, and t dash. Now t is not equal to t dash, therefore this alpha cannot be t. So the only possibility is that, let's say, I is equal to j, and alpha is equal to I, or alpha is equal to q plus I. Now, what we know is that xy is an edge in the graph, right? When xy is an edge in the graph, and by definition of mu t, right? By the definition of mu t, if mu t of x comma I is going to be I, then it is only because the distance was either 0 or 2. Similarly, it is q plus I if the distance was exactly 1. Now that says that the distance from v star to x and v star to y are going to be at most 2. But xy is adjacent, and v star to x and v star to y distance is at most 2, means that there is going to be a cycle of length less than or equal to 5. But which contradicts the choice of G. We said that the girth is at least 6. So therefore, this is not possible. Okay. So that is the contradiction. Okay. Now, as a consequence, we also should have, for some t star, psi of mu t star is equal to t star. And why is this? Because this number of colors that we have chosen is strictly more than c by 2. And just look at the colorings that are possible, right? So mu t of x comma I is I, q plus I, or t. Now what we said is that this color for at least one of them cannot be equal to t. Cannot be equal to I or q plus I, because if I or q plus I are taken, I ranges from 1 to q, and q plus I ranges from q plus 1 to 2q. So there are at most 2q possible colors that I can give from I or q plus I. But we have more than 2q guys in the set. So therefore more than 2q choices are there. But then mu t can be given only the colors I, q plus I, or t. If it cannot be given I or q plus I, it must be equal to t itself. So for some t, we know that psi of mu t is equal to t itself. So choose that and select it to be t star. Okay. So so far we have defined these maps psi, which are not simple maps. And now we are going to define another. What happened? Okay, another map. Something is missing. Okay. Another map, theta, which is a simple map. So so we know that, like, since we choose more than half of the colors, like 1 to 2q comma t star is exactly half of the colors. And for v star, we know that there is strictly more than half the colors will make IV star be large. So since this set 1 to 2q comma t star is strictly larger than not strictly larger than, it's equal to c by 2. at least one of the colors in this set must be making I V star B star large. So choose that to be B star. Okay. Now once you choose this particular color, then define theta in as a simple map where theta of x is V star if distance of in G of V star and x is greater than or equal to 2 and equal to T star if distance is less than or equal to 1. Again, this theta is very carefully defined because or carefully chosen, and you can see that the distance in V star and x is less than or equal to 1 for T star, and if you look at mu T definition, it is the distance is at least 3. So this is just to make sure that we can fine tune some more arguments. We will see the use of that now. So the claim is that now mu T star is adjacent to theta. Now, if that is not the case, what we do is that, well, as in the previous argument, there must be xi adjacent to yj such that theta of xi is equal to mu of yj. And mu T star of yj. Okay. Now, let us call this as alpha again. Now, alpha must be an element of B star T star intersection 1, 2, 3, etc. 2q comma T star. But this intersection is equal to T star, and therefore theta of x is equal to T star implies that the distance from x to V star is at most 1. But then according to the definition of mu T star, right, mu T star of y is equal to T star implies that the distance is at least 3. Now, if from y the distance is at least 3, it's actually in the second part it is V star comma y. Okay, so the distance from V star to y is at least 3, and distance from V star to x is less than or equal to 1. Then xy cannot be an edge, right? Because if xy is an edge, then the distance is at most 2. So that contradicts the choice of this thing. Therefore, x and y cannot be adjacent. So theta must be adjacent to mu T star. So okay. So once you have this, like we have almost all the things that we need. Okay. Now the observation is that psi of theta is different from psi of mu T star, implies psi of theta is equal to B star, because theta has only 2 possible choices, right? Either B star or T star, and psi of theta is an element of image of theta, right? For any function, we said that psi of phi is an image of phi, right? So therefore, since they are adjacent, they must be getting different colors, and since T star is going to get T star according to going to T star under psi, right? That's what psi of mu T star is equal to T star. It must be the case that theta is going to B star because they are adjacent. Okay? So yes. Now the claim is that, so once we have taken care of V star, now we are saying that, okay, not just V star, there is another vertex, let us say x, which is different from V star, such that the simple maps in I of V star, B star, let's say phi of x is an element of B star or T star. So phi of x has only 2 choices. So the color of x, which is in I of V star, B star, has only 2 choices, either B star or T star. And why is this? Well, what we know is that psi of phi is equal to phi of V star, and phi of V star is B star, right? By definition of IV B star, right? Phi of V star is B star. But now that implies that phi cannot be adjacent to theta, right? Because theta is going to B star. So if theta is adjacent to phi, then the psi will not be proper. So now let us take if they are not adjacent, that means that again, as the previous argument, there is some edge xy in E of G0. I am considering 0 because x could be equal to y, and and such that phi gives x the same color as theta gives y. Right? Now, if x is different from v star, we are done. So assume that x is equal to v star. So x is equal to v star, then theta of y is equal to phi of v star is equal to v star. And what about the distance according to the definition of theta star? Y comma v star, the distance must be at least 2. But now that contradicts the fact that, because v star is equal to x, the fact that the distance from x and x to y is 1, they are adjacent. So therefore, this is a contradiction, and x must be different from v star. So now we have this special vertex. Now let us say x different from v star. So I'm going to count I of v star b star in another way by saying that, okay, define Jx to be the set of all simple maps in I v star b star such that phi of x is in b star comma t star. Okay, so I'm going to count this by putting them, grouping them together with this property. Now we already know that like every phi must appear in one of these things, and by the previous lemma, phi belongs to I of b star for some, is appearing some of the jx, because we said that for every phi in I of b star there is some x with this property, right? So it must appear in some jx. So now I can count with respect to jx. So therefore now I of b star is now union over all x other than v star jx. And what is this? Well, jx, how many colorings can be there in jx, right? In v star b star, like v star is taken by every function in I of v star to just b star itself, right? So because phi of v star is equal to b star by definition of I of v star. So there is only one choice for the color of x, color of v star. And for the vertex x, we said that there are only two choices, because phi of x must be either b star or t star. But other n minus 2 p minus 2 vertices can have any possible c colors. So therefore, cardinality of jx is at most 1 into 2 into c raised to p minus 2. Now you can use union bound. So union over all these p minus 1 vertices, you will get at most 2 into p minus 1 into c raised to p minus 2. But this contradicts the definition that I of v star was large, right? If it is large, then it should be strictly greater than. So that is a contradiction, and that's what we are looking for. So this proves that there cannot be a proper coloring psi with c colors, and that is exactly the proof. Okay. Yeah, so we are done. And I just want to make a comment. I think I forgot to add this in the remark, that after this paper was out in the last April, this April, in 2020 April, Suding came up with an improved result, saying that there are graphs. So with chromatic number 225, and on number of vertices is something like 10,992 or something, and 30,337 or something. Okay. So on these many vertices, there are two graphs G and H, whose product also violates the Hedetniemi conjecture. So this is this is a result he wrote from this, and that's it. Thank you. If you have any questions, please feel free to ask.
Just one thing, sir. Here, this recent paper of Cloud13, which talks about two graphs with the chromatic number 15 or so, whose product has chromatic number 14. That's a
really?
very recent paper. Yeah, that's a very recent paper. And based on the same kind of stuff that Shitov did. This is a paper of Cloud13.
Okay. I will take a look. Thank you.
Yeah, that's it.
Are there any other questions or remarks? Anything from the audience? Okay, if not, then let's all unmute ourselves and thank the speaker.
Thank you.
Thank you, sir. It was really like talk on a very recent topic, which was actually open for many, many decades.
Yeah. I mean, thank you for this, and I hope it was interesting to at least some of you.
Yeah, even this paper was really tough to understand.
Yeah, very short paper, but
the proof is actually simple, but the way he has written it is very, very difficult to parse it unless you spend time to work out all the details.
Sure.
And I was very lazy, so since shooting did this job, I was very happy. And apparently, I'm not alone, because shooting said that he is giving this talk because several people have requested him to present it because they don't want to read it themselves. So, so anyway, okay. So
Yeah, thank you for the talk.
Yeah, thank you, sir.
Yeah.
Okay, so we'll meet next week again, but the timing is different for the next week. The speaker for next week is Anton Doctorman from Texas State University, and the talk is at 7:30 p.m.
Okay.
Okay, so we'll meet